Good morning, everyone, and welcome to IGTV. We've got with us William H. Murray for the InfraGard editorial, and Bill is going to be talking about expression of security requirements. Go ahead, Bill. Take it away. We're all eagerly listening.
Morning, Joe. The ancient Romans made the engineers stand under the bridge while the troops marched across. That's called having skin in the game. Bridges do fall down. Planes do experience uncontrolled flight into terrain. Still, I would gladly trade their record for ours. The results that we have produced in building, using, and maintaining secure systems are not as good as those produced by such traditional disciplines as civil engineering or aeronautical engineering. At least for purposes of discussion, grant me that the problems that these disciplines deal with, like keeping 40,000 pounds of airplane in the air, are at least as difficult as that of secure systems, and that their results are consistently better. One of the reasons that we do as poorly as we do is that we have not yet learned to express our requirements. For example, while engineers tell us that if we cannot measure them, we cannot recognize them, security requirements are often expressed in a binary manner. No give. Moreover, we often, not to say usually, put them on a separate list from the other requirements of the system. One way in which we have tried to describe security requirements is to say the system must enforce the policy. This might work if the policy to be enforced is really a security policy, that is, a statement of management's intent about what is to be protected, who is to protect it, and how much cost or risk we are prepared to accept in the process. However, we've traditionally gotten into deep trouble when we confused access control policy with security policy. For example, one anecdotal and perhaps apocryphal failure implemented the Bell-LaPadula model as though it were a security policy. The system failed because not only did it not provide overrides, on which the model is silent, but it provided no controls for relabeling objects or changing a user's privileges. These things were done offline while the system was down and the enforcement ineffective. But you could not write down. Requirements must be expressed in terms distinct from the mechanism to satisfy them. For example, resisting leakage is a requirement. Access control may be the choice of means to meet it. Resisting spoofing of the authentication process and eavesdropping of the response is a requirement. Trusted path is a means. Resisting replay of credentials is a requirement, while one-time password is a mechanism. Evaluation criteria are not requirements. Building to them is security by compliance, sometimes effective, rarely efficient. For example, the TCSEC, the Trusted Computing System Evaluation Criteria, enumerated evaluation criteria. These were often used as a shorthand for requirements. It was not unusual to hear or read, System X requires C2 security. As a shorthand, that might not have been too bad. However, this expression often short-circuited the real requirements process. The real securability requirements never got expressed, much less balanced against the other requirements of the system. In 2002, I participated in an AXA workshop on the application of engineering principles to system security design. Perhaps the most important idea to come out of that workshop was in a paper by Amund Hundstad and Jonas Hallberg of the Swedish Defense Research Agency. The paper was entitled Design for Securability, Applying Engineering Principles to the Design of Security Architectures. Said another way, the requirement of interest is not for secure systems, but for systems that can be configured, managed, and operated securely, for securability. Requirements for securability describe the environment in which the system must operate, including natural and man-made hazards and threats, the market or market conditions, the results that the system must produce, for example, move passengers and freight, perform computing applications, including user programming, performance, examples, passenger load, range, and speed. In computing systems, number of users, standard operations per unit of time, how the system must function, required and forbidden controls, for example, override of automated controls, the granularity of the controls, for example, flap settings, or the number of named users or resources. Control must be sufficiently granular that one can implement the rule of least privilege. Requirements for securability include things that the system must not do. For example, stall near cruise speed, or leak information between user compartments. Specific threats that it must resist, for example, lightning, or easily anticipated abuse and misuse, hostile use of controls, classes of attack. Microsoft has a relatively short list of classes of attack that it gives to its developers that they have to be able to resist. Strength, that is, the cost or force required to overcome whatever resistance we have otherwise built into the system. Note that strength is arbitrary. At the cost of other requirements, the system can be as strong as one wants. It cannot be infinitely strong. Design is difficult and choices are hard. And any other requirements necessary for completeness. The list implies that securitability of a system is a requirement that may be satisfied only at the expense of other requirements. Therefore, all of the requirements, securability or otherwise, must all be on the same table at the same time. Securability in a system is achieved at the expense of other desirable properties. Securability requirements have to be on the same list with such requirements as performance and function. Engineers caution us that requirements must be atomic, that is, as small as possible and independent of one another. When one requirement is unnecessarily bound to another, it eliminates possible designs, results in a requirement that is more difficult to satisfy than either alone, and moves that requirement ahead of some that neither would trump by itself. For example, requirement statements based upon the TC-sec often combine the requirements for isolation and mediation into a single requirement. This eliminated solutions that placed mediation in the trusted computing base, but not in the so-called kernel. DoD consistently rejected IBM's VM360 system because the access control facility, mediation, ran in a protected virtual machine rather than in the hypervisor, the mechanism that provided process-to-process isolation. Another fundamental engineering principle is is essential that we learned to talk in measurable terms, that we learned to talk about how much securability we want. The engineers insisted that if you cannot measure securability, you cannot recognize its presence or its absence. The tendency of security professionals to see security as either perfect or inadequate is not only incapacitating, but also destructive. In security, good enough always beats perfect. Said another way, one never wants security to be too good. Therefore, securability requirements should be expressed in measurable terms. For example, the cost to defeat them, the necessary work, access, indifference to detection, special knowledge, and time required to defeat a mechanism is a useful measure of its strength. It's far easier to build a system to resist an unauthorized outsider than one to resist a privileged insider. Security designers are often incapacitated by the challenge of the latter when the real requirement is the former. Knowing what we want and how much we are prepared to pay for it is only half the problem. The other half is expressing what we want and recording the expression in a form that enables others to understand what we want and the choices that we have made in such a way that they can build what we want and operate it in the way that we intend. We call that expression and description a specification. A specification includes a verbal description of how the system is to achieve the requirements, what functions it will perform, what controls and interfaces it will present, what it will look like, its appearance, a picture. For example, controls, screenshots, sample reports. What materials and components, both off the shelf or purpose-built, it will be constructed from. How it will fail, what failure modes are going to be present, indications of the evidence of failure. When the airplane stalls, we're going to get a stall warning, both in a sound and in the shaking of the yoke. A model or prototype, a user's or operator's manual, assembly processes, how are we going to put the components together, test data and demonstration procedures, and anything else necessary or useful for complete communication. Now, notice, test data turns out to be part of the specification. It's not something that we do after we have built the mechanism. Now, this talk this morning is at best a gloss. It includes examples, but limitations of time and medium ensure that it is less than complete. I've addressed what we need to know and do, but have stopped far short of telling you how to do it. Identifying the requirements and choosing between them is hard. Design is difficult. If we are to include others in our endeavor, expressing those decisions is essential. However, the knowledge, skills, and abilities implied by all of this define us in part as professionals and earn us the big bucks. Now, I've provided a link in the chat to a paper that goes into all of this in a great deal more detail. Joe, have you got that link?
Yeah, it is up there, and actually, to my delight, Phil, as you went through this, and I think you had your professor hat on here, so I'm going to have to review this once or twice more, because you actually got into some pretty deep stuff here. All right, Phil has put up 2 links as well, and the first one, the design for securitability. And the second one is the WAEP SSD Working Group 2 report, a report on the activities of 1 or 2 groups formed during the ACSA workshop on application of engineering principles. All right, and of course that's by you.
The papers, of course, go into this in a great deal more depth. I think this idea of securability is a very important idea. That we don't build safe airplanes. We build airplanes that can be flown safely. And the same thing has got to be true of our systems. We build systems that can be operated, managed, and used safely. But if we want them to be safe, and safety to trump everything else, of course, we either have infinite cost or zero other utility.
Yeah, well, I'm with you there. I'm going to review this one, Bill, because this one's worth looking at the papers. All right, I've got John coming right behind you, so I've got to go.
Okay.
All right, great talk. All right,
see you
bye
next
now.
week.
Yep.